Welcome back, class. So today we are going to start our exploration of Chapter 6. In Chapter 6, we'll be sort of shifting our focus a little bit, and we'll be focusing exclusively on one particular state of matter, and that is gases. So you might remember our basic discussion about gases from Chapter 1 when we categorized matter by the states of matter, whether they were gas, a liquid, and a solid. So let's begin by talking about some of the very fundamental properties of gases that we mentioned originally back in Chapter 1. So first of all, if we think about the shape of a gas, right? Gases have non-definite shape, and they also, if you remember, have a non-definite volume. Essentially what that means is they will fill the space provided. Right? So you put a gas in a container, it will fill the provided container, right? It'll occupy that shape of container, and it'll fill that volume of container, whatever that happens to be. Now, we also talked about gases being compressible. Now, remember, what compressibility means simply is that gases can be pressed or squeezed, if you will, into a smaller volume. Think about using a piston to reduce the volume, and now the gas will occupy that smaller volume or expand to a larger volume. Or taking a balloon and squeezing it with your hands to reduce the size, right? The gas will occupy that smaller shape now, right? We can squeeze a balloon, right? It's compressible. The other two states of matter, solids and liquids, are non-compressible. So that's one unique property to a gas. Now, that's related to the density of gases, right? Gases have low density. And what that essentially means is that there's lots of empty space. So we're going to talk about this a little bit later in this video. We'll sort of expand on this idea of the low density of gases and how there's lots of empty space in a sample of gas. And lastly, gases have kinetic energy, right? Similar to what liquids and solids have, but even to a larger extent, we can think about the kinetic energy of gases. So we think about gas particles as being in constant motion. And this is proportional, this energy, right? The kinetic energy is proportional to the Kelvin temperature, right? The absolute temperature. And so we'll also expand more on this idea of the kinetic energy being proportional to the temperature. Okay, so these are some of the basic properties, and we'll see these come up, especially the last two, as we go through various aspects of gases. Now, when we think about studying gases, we want a theory to sort of base our studies on. And the simplest theory of gas behavior is what's called the kinetic molecular theory. And essentially what it proposes is that a single particle, so we think about gases as a bunch of single individual particles, move in straight lines until they collide with either the walls of the container or another gas particle. Now, we can sort of think about this with three main arguments or three main tenets of this theory, right? If we think about the first one, and that is that particle size is negligibly small, right? The actual particles of the gas occupy about 1/100th% of the volume of the gas sample. So 0.01% of the volume is actually coming from the actual gas particles. Right? So this goes back to the idea of lots of empty space. So in other words, 99.9% of the sample of a gas is essentially empty space. When we think about, normal sort of standard, normal conditions that we would operate under, if you will. This ties into the concept, that we talked about on the last slide of low density, right? There's a lot of empty space that is connected to the idea of low densities for gases. The second sort of key point here is that the average kinetic energy of the gas particles is proportional to, again, the Kelvin temperature. So that's what we were saying at the end of the last slide. And I'll point out that notice the temperature is proportional to the kinetic energy, not the velocity. So not the speed of the particles, which is something we often say, which is we say, well, we heat it up, the molecules are moving faster. Well, that is true. It may be true. The proportionality is actually between the temperature and the kinetic energy of the molecules or atoms. And thirdly, the collision of a particle with another or the walls of the container, right? The collisions are what we call completely elastic. And what that essentially means is that when they collide, they may exchange energy, but there is no loss of energy. So we often envision these gas particles colliding more like if you had billiard balls or ball bearings, right? Hard objects colliding and they bounce off each other, right? They can exchange energy, right? So one of the particles that's moving faster could hit in one and exchange some energy, but there would be no loss of energy. It's complete exchange. In other words, the molecules don't stick together, right? There is no stickiness. They hit each other and bounce directly off like we think of, again, with sort of very hard spheres as opposed to something like, marshmallows colliding or clay colliding, right? Where there's sort of a distortion of the shape, etc. So the attraction between the particles is negligible. They don't stick to each other when they collide. They just hit each other and bounce off. Okay. So what we discuss going forth when we talk about gases is all going to be governed under these assumptions, right? We're going to assume these types of behaviors or these ideas are being followed. So let's talk a little bit more about this idea of the low density of gases and how that comes into play. So let's think about, for example, liquid water, right? And we know liquid water has a density of right around 1 gram per milliliter. And what if I want to calculate the volume of 1 mole of water? So let's remind ourselves that density equals mass over volume. So we need to know the mass of 1 mole of water. Well, if we have 1 mole, that's simply going to be its molar mass, right? So for water, it's going to be 18.02 grams per 1 mole. And we're going to try to find, right, the volume. Right? So if we rearrange this equation, volume is equal to mass divided by density. So if I go ahead and do this calculation, I'm going to take 18.02 grams and I'm going to show it this way so we can follow the dimensional analysis. So we're going to divide by the density, which is 1.0 grams per 1 milliliter. And this, my grams cancel, and I end up with 18.02 milliliters as the volume for 1 mole . One mole of liquid water. Now, what if I were to sort of hypothesize, or just sort of say that if the same amount of water were occupied 22.4 liters, what would its density become, right? So what would the density be if that same amount of water occupied 22.4 liters? Well, again, we're going to go back to our density equation here. And so our unknown density is going to be our mass. So it's the same amount. So we have 18.02 grams. And our volume here is 22.4 liters. So if I do that math, reduce it to 3 significant figures, we get 0.804 grams per liter. Now, to make this a little more comparable, we can convert this to grams per milliliter. And so, if I do that, right, I can do my 1 times 10 to the minus third liter is equivalent to 1 milliliter. So my liters cancel, and I get 0.000804 grams per milliliter. Or, if you want to write it in scientific notation, a little easier to see, 8.04 times 10 to the negative 4th grams per milliliter. So what we can see here is if the same amount of gas were allowed to occupy a much larger volume, of course the density would go down. Now, it turns out that this volume, 22.04, is the volume occupied when 1 mole of gas, or 1 mole of is the volume occupied when 1 mole of gas exists. Right? So if this water were to evaporate into a gas, it would expand to occupy 22.4 liters. So the 22.4 liters is what we call the molar volume of a gas. So the molar volume is the volume occupied by 1 mole. Now, we're just going to say we're dealing with gases, so we're going to specify the volume occupied by 1 mole of a gas at STP is 22.4 liters. So the calculation previous page estimated that when 1 mole of a gas occupies this relatively large volume, it has a very low density, right? Explaining why gas samples have this very low density, lots of empty space. Now, what are standard conditions? Well, we have to specify conditions, and so when we call these standard conditions, these are just sort of agreed upon conditions that we can compare values at. So the standard conditions for a gas are 1 atmosphere of pressure, which we'll talk about later, what I mean by pressure, at 273 Kelvin or 0 Celsius. So when we're doing a problem and we talk about standard conditions or STP conditions, this is what we're talking about. And so the volume of a gas at STP is 22.4 liters, right? So, and it does not depend on the gas. So it doesn't matter what the gas is, whether it's helium or xenon or methane. If you have 1 mole of it at STP, it will occupy the same molar volume, 22.4 liters. Now, all of these gases have different masses, of course. So these balloons, while they all might be the same size, would have different masses. And therefore, the densities are going to be different, but the volume will all be the same. It's the masses that would be different. So a little bit more elaboration on this idea of gases having low densities and occupying, large volumes with lots of empty space under sort of normal conditions. Now, let's turn our attention to the last point that we had on our basic table, and that was that the kinetic energy is directly proportional to the temperature, or is proportional to the Kelvin temperature. So let's think about some things before we dive into this, right? So if we think about a gas sample, so a gas at a given temperature, we know that all the particles have the same temp. Right? So we have the temperature, they're all at the same temperature. Now, if we look at this equation for the kinetic energy, it tells me that the kinetic energy is equal to 3/2 R, which is a constant, times temperature. So what this tells me is that as the temperature would increase, the kinetic energy would increase, so that gases in the same container have the same temperature, and therefore they have the same kinetic energy. So all the particles, all the gases have the same kinetic energy. Now, what about velocity, right? The speed, right? We have to say, we heat up a gas, the molecules move faster, the particles move faster, right? So if we look at probably a more well-known equation for kinetic energy, that the kinetic energy equals 1/2 the mass times the velocity squared, we can see here that if all the particles have the same kinetic energy, right, then that means particles of different masses have to have different velocities, right? So if I have a mixture of gases, for example, and my masses are different, the only way that they all can have the same kinetic energy is if they have different velocities. So what this tells me is that because they have the same average kinetic energy, that heavier molecules must have a slower average velocity. Because if m gets bigger here, if m gets bigger in my equation, then that means in order for kinetic energy to be the same, the velocity must be smaller. So what this tells me is that velocity is inversely proportional to mass. Now, since we're going to deal on molar quantities, right, we can say it's inversely proportional to molar mass. Okay, so what does this do for us? Well, let's look at this graph first of all, and we can clearly see this in work here, right? If we look at various gases, we see that as the gases get lighter and lighter, right? So we got heavy gas, oxygen here, which has a molar mass of 32, right? Has an average velocity under 500 meters per second. You get out to something like helium, right, which has a mass of about 4, has a velocity somewhere over 1,000, right? Between 1,000 and 1,500. And you get out to a really light gas, like hydrogen, you start getting average velocities close to 2,000 meters per second. So clearly, as the mass is going down, the velocity is going up. Now, the other thing to point out here is that this is an average velocity, right? So not all particles, even with the same mass, are moving at the same velocity, right? So just like we have, it's an average kinetic energy, this is an average velocity. Now, how can we put all this together? Well, we have this equation here that we can generate. Now, I'm not going to go into the detail of the book, but I'll just quickly point out that if we take these two kinetic energies equations, mv squared equals 3 halves RT, and we allow mass to become molar mass. We deal with we're going to deal with moles, and we solve for this, we get, so if we solve for v for velocity, we get the velocity equals the square root of 3RT over the molar mass. Now, this is a special velocity. This is called the root mean square velocity, and it's a special kind of average velocity that we use when we talk about gas particles, right? For our purposes, we can just think about it as the average velocity of the particles, right? It's just how that average is established. So we have this equation, right, now that we can relate velocity to temperature and to molar mass, right? And we can see here that velocity and the inverse relationship to molar mass, right? We can see that in this equation, as mass gets bigger, right, it's because we're dividing by it, then that means the velocity is going to get smaller, right? The answer is going to get smaller. Now, we could also see, if we look at the second graph here, that as we take the same gas, so the same molar mass, but we raise the temperature, notice what happens to the velocity. The velocity goes up. And what we're seeing is what we see in the equation here. Right? We're seeing that the velocity is directly proportional to the temperature. So if I increase T, because it's on the top here, my answer and everything else remain constant, so my velocity is going to go up. So what we've established here is that velocity is inversely proportional to mass, to molar mass, and directly proportional to the temperature, the Kelvin temperature. So, just to summarize here, if a gas at a given temperature, right, all particles are considered to have the same temperature, that means that all particles will have the same average kinetic energy, but they don't have the same velocity. That will vary with mass. Okay, well let's try a little sample here. Let's do an example calculation here. So let's look at our equation here, and let's remember what we concluded here. So we concluded, based on this equation, that the velocity, the root mean square velocity, is directly proportional to the temperature, to the square root of temperature, right? So as temperature goes up, velocity goes up, and the velocity was inversely related to the square root of the 1 over the molar mass, so we got that inverse relationship. So as molar mass goes up, velocity goes down. Right? So those are two things we can get directly out of this equation. Now, a couple of things when working with this equation that we need to keep in mind. First of all, the temperature is in Kelvin. Now, and because of the units, and this is strange, it's a little different, the molar mass here needs to be in kilograms per mole. And this is to make the units work, and I can talk about that in a second. So let's just talk about generically, right? If I were just to look at this equation conceptually when answer a question, if the temperature is doubled, what happens to the velocity? Well, based on what we can see here, right? If I raise t, velocity goes up. So it is true that as I raise the temperature, the velocity will increase, right? The average velocity, right? We're always talking about averages. We're talking about collections of huge amounts of molecules here, and so, we state an average. Some will be a little bit slower, some will be a little bit faster, right? So we saw those graphs, those curves that show that, not every molecule is at exactly the same velocity. There's a spread. Now, what about we actually calculate some stuff? So I'm just going to do one of these. I think that'll be enough. But we could go ahead and do different temperatures, right? So let's say we wanted to calculate the root mean square velocity of neon at 25 degrees Celsius. Well, first thing is we need to understand that 25 degrees Celsius, right, is really 298.15 Kelvin. So we're going to convert to Kelvin temperature. And so if we go our equation, the root mean square velocity equals the square root of 3 times 8.314, and that's joules per mole Kelvin times 298.15 Kelvin. The molar mass. So neon has a molar mass of 20.18 grams per mole. So that's going to be equivalent of 2.018 times 10 to the minus second kilograms per mole. So, just make sure we follow along here. So I did 20.18 grams per mole times it by that 1 kilogram equals oops, sorry. And I erased it, wrote that wrong. Grams, kilograms here. So 1 kilogram, 1 times 10 to the third grams. So this is where we get 2.018 times 10 to the minus second kilograms per mole. Grams cancel. Okay, so if I plug all this math in here, I get 607. If I do it to 4 significant figures. So let's plug that in. So we get 3 times 8.314 times 298.15 divided by 2.018. -2. And as I do these, make sure you're following along. Make sure you can see the calculations. Make sure that you're coming up with the same answers. And so here, let me do this a little more detailed just so you can see it. So if I were to do this, I get the square root, of 3, 6, 8, 5, 0, 6, into the square root, 3, 6, 8, 5, 0, 6. And we, again, keep this to 4 significant figures. I get 607.0 meters per second as my velocity. Now, I want to look about at the units real quick here. So I came up with units of meters per second, which is what you should, right? These are the units of velocity, but it's not really clear necessarily how we come up with those units. So we need to follow dimensional analysis, of course. So if I look at this, I can see some of it, right? I can see clearly that my Kelvin cancel out. I can see I have division by moles here, and I have division by moles here. So my units here, right, are joules per kilogram. Okay. Well, how does joules per kilogram become meters per second? Well, let me take you to follow along a little bit here. So first of all, I'll do it down here. We have the square root of joules over kilogram. Now, a joule, right? A joule is a complex unit, right? A unit of energy, and it's equivalent to a kilogram times meter squared over second squared. So it's a mass times an acceleration. So if I go ahead and make these substitutions, so I have a square root of a kilogram times, so you might think about our mass times velocity squared, right? Like our kinetic energy equation, right? M times v squared, right? So this is what the units are. So it's a mass times a velocity squared over second squared divided by kilograms. So if we follow along here, we can see that the kilograms cancel, and so we end up with the square root of meter squared per second squared. And of course, if we take the square root there, we end up with meters per second. And this is how we get units of velocity out of this whole math thing. So while sometimes the units are not crystal clear, if we break it down and we follow along, we can see that we are indeed getting the correct units in. We do indeed get a velocity out of here. All right, so we're going to bring this section to a close and just emphasizing these fundamental relationships that we're starting to see, right? That the average velocity, right, is dependent on the molar mass of the material, right? Inversely proportional. So bigger molecules have slower average velocity. The average velocity is dependent on the Kelvin temperature, right? So the higher the Kelvin temperature, the higher the velocity is going to be. And the higher the temperature, right, the higher the kinetic energy, the higher the average kinetic energy, right? That's what the kinetic molecular theory, that's what the original starting point was, that the higher the average, the higher the temperature, the higher the average kinetic energy. And then now we can see that the higher the average temperature, the higher the average velocity as well. All right, so next time we will be looking at other aspects of gases, including pressure and simple laws of gases.